all, thank you for your interest in our talk. I'm Pavithra and I'm a senior data scientist. I lead the NLP and computer vision work stream at Great Ormond Street Hospital, NHS Trust. And with me, we also have Sebin Sabu, my colleague. He's the NLP and ML engineer who's responsible for building the ML and NLP pipelines at Gosh. So today we would be discussing about the capabilities of large language models and few short learning approaches and in the context of cardiac MRI data. So just to give you a bit of an introduction, Great Ormond Street Hospital, we are a pediatric hospital where children and young people with rare, complex and difficult to treat conditions are treated here. And we are also the first biomedical research center along with UCL. And myself and Sebin, we are part of the digital research environment team, which is a part of Gosh Drive, which is the innovation hub for the trust. And I would like to thank my entire DRE team. And we also have a 5-year partnership with Roche, and some of the work that we present here are part of the deliverables that we do with them. So just going on into the topic, why unstructured data? So when we discuss with some of our clinicians as to why are we looking into these unstructured data, what we found was that there's so much of large volumes of unstructured data locked within our electronic patient record systems. So this could be in the form of text, test reports, discharge summaries, images, and all these contain valuable routine information that is not currently present within the available structured information. And clinicians and researchers, they would often want to perform a retrospective analysis on these patient cohorts as part of the clinical decision-making process, or even want to use this data for secondary research purpose. So let's say, in context with the topic that we are going to talk today, a clinician would want to know how many people or how many patients were diagnosed with tetralogy of Fallot. And to be able to do this currently, a clinician would have to manually go over all these unstructured reports because this information is not present as part of our existing structured data. So what do they do then? They would have to follow a manual process, which is a timely process. It might require someone with the domain expertise, and also they would have to ensure that they capture all these information manually into a structured form. Sorry. And so even if they do this, they would have to do it on a very small subset of data. So they can't scale it up to a large volume of information. So what do we do here is we would want to enable an automated extraction of these information from large volumes of unstructured information, that is the information present in these cardiac MRI reports. And by doing this, we believe that it would help to answer a lot of clinical questions in a timely manner. It would help with the clinical decision-making process. It would also help in terms of data enrichment. So by providing this information, we are able to capture the data that's not present in the existing structured information, and this could be used for the research purpose. And this is not just restricted to text. We would find this type of information also present in other modalities like images. Now Sebin's going to focus on the use case and he will discuss about it.
Hello, thanks, Pavi. So, one of our focus was, is it possible for information extraction in a hospital context using natural language processing? So, because the hospital have a lot of reports which were accumulated over a long period of time with a lot of very valuable clinical data, which is not available in a structured format. So it's impossible for us to do any clinical studies on top of them. So one of them is a cardiac MRI reports. It's almost like 15,000 reports, which were produced over a period of 10 years by different consultants. So basically, it's consultants creating PDF reports out of their clinical tests and evaluations. It contains a lot of measurements in tabular format and some text information. Since it's been created over a long time by different physicians, it's in a heterogeneous nature. Like it's not in a very structured or homogeneous format. Most of the clinical measurements they have done over the time is very valuable for researchers in precision medicine or drug discovery or some certain cohort-based studies in the cardiac domain. So we believe that once we are able to extract those information over that long period of time, the impact will be very higher on that. So one challenge we faced when we start with this work, since we will be processing a very large set of data, is that we don't have a strong infrastructure to do that. We cannot rely on our laptop for this process. So we have to figure out an ecosystem inside our unit to process work like this. Since it's an NHS trust, we have to consider the information governance very thoroughly. So we came up with a solution called Grid. Grid is basically two Linux servers. One is a development server, which have access to the internet, but we are not permitted to process any patient data on it. And the other one is a staging server, which is disconnected from the internet, but we can process the pipelines on patient data. So the flow is we create pipelines and components inside the development server and run on the patient data in the staging server. Grid was very crucial for this work because it pulled down the processing time from days on a work laptop to few hours. So it was a very crucial for this work. Yes. Next slide. Okay. So this was the so this gives an outline on what was the challenge and what was the challenge we were facing on information extracting from the CMR reports. For giving an outline, it contains almost like 10 years of data. So necessarily they were not following a very strong format over the time. So we used the capabilities of large language models as a question answering tool on this purpose. Since the data is heterogeneous, we were not able to use traditional NLP techniques because we would have to accommodate all the changes, and the development and the reliability of that will be a big challenge. Large language models were able to absorb the heterogeneity of the data without much development overhead. So we used smaller large language models because since we don't have access to GPU power as for now, we are using CPU powers. So our set of LLM models to be used was like small. Um, what we did was, for example, say Flantify large, we asked a question like what is the patient's name on providing a context, which is an unstructured chunk of text from the reports. So the LLMs were successful on extracting the entities from this unstructured text. So the one of the crucial nature of this extracting patient identifiers is we will be able to link up these structured data with the other data points which our unit is already successful in providing. We have one of the largest data points available in the UK in a structured format for research and analysis. So these 15,000 reports will now be able to link up with the other structured data that we are providing. So we did some evaluations to see which kind of models are suitable for our work. We were able to observe some very interesting findings. I have avoided reporting some of the models which were hallucinating and was not at all giving a good result. One of it is Flantify Small. The performance of Flantify Small was like very low, like it was hallucinating a lot. So there were like no valid report to present at all. And you can see that the performance of BERT is less than the other ones, and the Flantify Large was given a very good result. The other study we did was to include a prompt which will give context to the large language model about what is the report. Like this is a part from an cardiac unstructured text in a cardiac MRI report in the Ghosh Hospital. So we observed that by providing that prompt, performance of the models on extracting entities like a name or the reference name has increased significantly in Flandy 5 and Robota. But some interesting results we obtained from BERT, which was the performance dropped significantly on extracting MRI numbers and NHS numbers. So in one of the some of the literature review, we found that there are some studies which suggest that BERT kind of suffers on extracting very large numbers. So most of the NHS numbers and MR numbers are actually very large numbers. So this might be a reason for that. But still, why there was a performance drop on adding the prompt is an open question for research. I think there will be a really good reason behind that. So we did studies to like the attribute score for the integral gradient to observe what happens inside the model on when we provide a context or not. So in this case, you can see that the model's ability to conclude towards picking up the name of the patient successfully has increased very much when we give the prompt. So it was confused on picking up different names when there was no prompt. So the one example must be even we can see from this chunk of unstructured text that there are names about the name about the clinician, there's the patient name, and there's the hospital name. So unless we provide a context that is an unstructured text from a report of a patient in the hospital, the model is not getting the proper context that which name it should prioritize. So I think this is a really good finding, which shows about the importance of providing the context. We did the study on insect on Flandy 5 large. Yeah.
Thank you, Sebin. So the next pipeline, once we've extracted the patient entities, was what about the other information? So these CMR reports contain a lot of measurements, lots of tables. So what we did was we started with a rule-based approach. Like, can we just extract the tables using rules? But it wasn't. We weren't able to scale it across the 10 years of data. One was the heterogeneity in the data. The other one was when we extract these tables, when we detect the tables from these PDF documents, we found that a lot of incorrect information were captured as tabular information that kind of reduced the performance of a rule-based approach. So the next thing what we did was we knew that there is less variation in the data, but there was a consistent pattern among the tables. So each table sometimes would be merged, but they would have a header value followed by the rows containing all the values or measurements. And what we did was we wanted to train a classifier using a very small annotated data, more of a few shot learning approach. And what we did was we annotated each row in a table as whether it is a header row or is it a value row or is it something that's been captured incorrectly. And just to give you a few examples, these tables contain like ventricular volume measurements, flow measurements, pulmonary diameter. So lots of values, lots of measurements and numbers that has to be captured accurately. So what we did here was because we had a very few or a less number of examples labeled, we followed the few shot learning approach called setfit. It is kind of very popular. So what basically this paper the authors have done here is they've made use of the ability of sentence transformers. So they kind of generate sentence pairs based on contrastive training. They then fine tune the sentence transformer to be able to capture the representations of these examples. And these embeddings are then used in a classification head, a classical ML classifier. And then these are then used to classify whether uh, an example is of a particular label. And in terms of the experiments and result, we experimented with different sentence transformers. But for our example, we found that the digital robota model was able to provide the best performance. And we also used a hyperparameter search to pick the best hyperparameter values. And in terms of the classification head, we use the SVM classifier. So our annotated data was, we split them into 280 examples for training and 80 examples for validation. And on the left, if you can see here, I've just added the UMAP visualization of the embeddings of the examples in the training data before and after it's been fine-tuned. So as you can see here, once fine-tuned, the sentence representations itself, we could see that the examples that are related to non-relevant or incorrect information is kind of separated from the header rows and the value rows. So this kind of help in providing a good performance. So once the classifier has been trained, we then kind of validated using the F1 score. So this data was picked from the 10-year data. So we randomly picked it from across the 10 years just to keep track of the heterogeneity. And as you can see here, we can see a significant boost in the performance with the help of a few shot learning approach. So while the rule-based approach was able to do, but it wasn't up to the mark. So in cases like this, we do find that the set-fit based classifier has been able to provide us like very good results. And as future work, what we would want to do then is we kind of want to use all these components, reuse them for other reports, other use cases to see how generalizable it is. So, for example, if we take the large language models, these are not trained on our data, but yet they were able to provide us some good results. So, we would want to see if we can use all these general purpose large language models or domain specific large language models in a zero shot approach, how much are we able to utilize their capabilities. And also in cases where we do find that there's a pattern, but then we don't have enough variations like this table row classification, we do want to start using more of a few short learning approach. And I hope you enjoyed our talk today. Thank you so much for listening.